Thank you so much. Am I audible? So thank you very much to the organizers for inviting me here today to your lovely campus in ICTS, and hope all of you are having a good time in the summer school. I'm aware I'm the last talk of the day, so I hope you will find this interesting. I'm sure you have been working hard all day and all of the previous days on the different lectures and topics you have been listening to. So the talk for today is titled Models and Meanings. And this talk is about the area I work in, which is computational linguistics. And maybe some of you have not heard these two words together before, or maybe you have heard of each of them separately. But this idea that one could teach machines language has always fascinated us for many, many years. So this is a picture from a film called Frankenstein, which is based on a novel of the same name by Mary Shelley. And Mary Shelley is arguably one of the first early science fiction stories about this artificial being who was brought to life by this inventor whose name was Victor. And eventually, he began to learn language. One of the things he began to do was learn language by listening to the people around him. And then also he eventually started to read books and become quite proficient at language. So this is something that this idea of machines or artificial beings learning and speaking and talking like us is something that has fascinated us for a long time. Now, what is so interesting about language? What makes it kind of so effortless an endeavor for us to learn? And why is it kind of challenging as a field when it comes to teaching machines? Now, one of the things that all natural languages have is form as well as meaning. I mean, at a very basic level, when you think of the word cat, okay, cat has some symbols on the page, right? And it also has the form in the sense of the sound, k, t, right? And corresponding to that is its meaning, right? And the meaning is this cat that lives in the real world. It has whiskers and ears. And the cat sound is corresponding to this concept of cat, okay, which is a mammal, which is domesticated, right? And there's this, mapping between the form and the meaning. And together we then understand what we mean when we say cat, right? And one of the things that most kinds of models of language are very good at is capturing form. Okay, they can understand the structures of language. They can understand the sounds of language, and this starts from things like grammars. Okay, so if you think of any descriptive simple grammar of a language that you might have studied, right, for Hindi, Sanskrit, Marathi, it will have some basic descriptions about the language, right? Then what are the verbs, what are the nouns, so on. Maybe when you learned a new language, you had to get a simple description of what these things are. Other kinds of frameworks, like a grammar formalism, for instance, in language, takes as an input a sentence and gives you as an output a sort of structure of what is in that sentence. How many nouns, verbs, adjectives are there? How are they related to each other in terms of the syntactic relations of subject, object, and so on. And these will use some abstract operations like feature unification, or will define certain abstract operations to give you that output. So, and then you have language models. And language models are also very much trained on form. Okay, what I mean is that they will be trained on a lot of text that is taken from various sources, and then they come up with the representation of language, which is then used to generate sentences. But again, here, these are all, these are all focused, or they are very good at capturing form. Meaning, on the other hand, is a different story. Well, with meaning, there are different ways in which one is trying to understand meaning in language. One well sort of studied way is to use a meta language. Okay, so a logical meta language, which perhaps you have studied, like predicational logic or lambda calculus. That is one way to capture meaning. But that doesn't still capture the entirety of meaning. So then you have various other kinds of ways, like semantic networks or knowledge bases, all of which are trying to capture this idea that the concepts we have in our mind are not just isolated, right? They're connected to each other. There is also a whole lot of cultural and other specific knowledge that we are aware of. So all of this we can try and capture using some of these kinds of techniques. And ideally, the kind of language, the kind of model of language that you would like to have integrates both form and meaning. Okay, but this is what we'd like to do, but that's not always possible, or it is actually one of the challenges of computational linguistics, how to integrate form and meaning. And what are some of the other challenges that are there? Well, one of them is simply the fact that there are so many languages in the world, the challenge of multilingualism. So we have thousands of spoken languages all over the world. There are many diverse language families. So we generally group, like birds are grouped. The languages are also grouped into families. And there are as many as 4 to 5 different language families in India itself. India is also a highly multilingual country. And there are many different kinds of writing systems as well. So all of these kinds of differences are things that we need to take into account. So ideally, your model should say, well, it doesn't just work for 2, 3 languages, but most or many or all the languages. What else? Well, we have, within the same language, we also have so much expressivity, right? So one of our abilities as human beings, as communicators, is that we can take language and use it in a variety of domains, right? And that's something most other species can't do. So you can have simply dialogue, okay, where you're talking to each other and then you speak in a certain way, or really, or wow, and so on. You can have scientific writing where you use particular, let's say, technical terms, and then you're trying to talk, discuss a particular topic. You can have legal language, like the kind you find in contracts, right, which are specifying something very specific. You have language on the web. I know, right? Shaking my head and so on. This is very different from the abbreviations that you use will be very different from the things you will read in a news article, which is talking about a particular situation, reporting on a particular event, right? And so this expressivity is found across domains. So you ideally want to think of a system that doesn't just work on news, but also other kinds of domains. So that makes the task very challenging. The other, which is kind of one of the hallmarks of natural language, and which is not something that you would typically find in another kind of language that you may be working with, that is, let's say, programming languages, is ambiguity. Okay, so ambiguity is pervasive in language, right? So if you have starting from the word level, so if you have a word like mouse, mouse is an animal, right? It's also something that you use with your computer, right? Similarly, here you have a sentence, I saw a man with a telescope, okay? And that could mean I saw a man who was standing there with a telescope, right? Or I saw a man using a telescope, right? So there's ambiguity there. And one of the things that the way to resolve this ambiguity is to be aware of that larger context. But structurally or on the surface, the sentences are exactly the same. So those are some of the interesting challenges when it comes to working with language. To sort of give you a bit of a tour of the kind of approaches people have used over the years, I'm going to give you a sort of breakdown of the field into 3 eras, so inspired by Taylor Swift. So this breakdown is, of course, completely my own sort of slightly idiosyncratic division, but nevertheless. So let's say the first was the grammars era. And the grammars era started around the mid-70s and continued for a couple decades. And in the grammars era, basically, you had various kinds of computational grammars that were written. These were rule-based grammars. And they were pretty large. Like they encompassed all the phenomena of the language. Okay, so you had to write rules for relative clauses, for questions, for exclamations, for all kinds of embedded clauses, everything, right? And you had to make use of various operations like feature unification, specific operations like, in this example here, this is an example of substitution and adjunction, which is something that you see in a particular kind of grammar called tree adjoining grammar. And so what these grammars would do is, if I gave it a sentence like, Jill is running, it would figure out a way to break it down and give me a structure of that sentence, okay? As to what were the nouns, the verbs, and how were they connected to each other in terms of their syntactic relationships. And so in the grammars era, one of the things that was nice was that you knew exactly when your system sort of didn't work, because, well, you either didn't have that rule, you didn't write that rule, or you sort of didn't have that word in your vocabulary or something like that. And it was pretty clear to pinpoint exactly why that to explain exactly why things were working or not working. And in terms of being multilingual, well, there were some limitations, as in because you had to sit and write this huge grammar. So it obviously existed only for some languages and not all of them. Then around 95 or so, at this point that I have decided that the era ends, you had a lot of progress in the area of speech recognition. So you had statistical models that now were showing a lot of success in automatically understanding speech. Okay, these were called the IBM speech models. And people got really excited by this new development, and they said, okay, let's now try and apply this to text as well. So that took us to the next era, which was the linguistic structure prediction era. Okay, and that also sort of started around 95, where everyone was like, okay, great, let's do this machine learning. Let's use these models to also understand text processing. How do words, sentences, and to predict all the structure, which I was previously doing using those grammars. So one of the requirements of this particular time, or the way these models were set up, was that you had to have linguistic data or examples of, let's say, lots and lots of articles taken from some newspaper, to which you had to add some linguistic labels. So for example, if I wanted to learn the parts of speech, in a sentence. Then I took a whole lot of sentences from, let's say, the New York Times, and I added manually those labels to them. Okay. Then I took the machine learning model, trained them on these labels, and then when I was given some some text to which the model hadn't seen before, it would apply, it would sort of be able to predict the correct part of speech. Okay. And so you needed these linguistic data sets, but you could now predict structure at all different levels. So you could predict parts of speech, you could predict maybe the individual suffixes and affixes, you could predict things like the syntactic relations, you could predict things like co-reference. So for instance, if I had a sentence like, John went to school, he ate his lunch there, and I wanted to know what he referred to. What is he referring to? It's referring to John, right? So all these tasks I could do now using the annotated linguistic data and the machine learning model. And you were then able to do structure prediction, okay, in a sort of using stochastic learning. And in comparison to the grammars era, you had some loss in terms of explaining why things would work or not work. But there was still some scope of doing an error analysis to understand why the system is working or why it is failing. And in terms of multilingualism, well, again, you were constrained by the fact that, well, you had to have these data sets. So if you didn't have those data sets, then the machine learning models had nothing to learn from, right? So if you were trying to make this work for a lot of languages, then you needed to have data sets in all of those languages, right? So that was another constraint. Although people were then gotten pretty excited about the potential of this, and then you had a lot of efforts in creating this kind of labeled data sets. And one of them is universal dependencies, which came out of this era. And sort of the peak of this era, in my mind at least, is this particular challenge that was where a machine played against some human participants in a quiz game called Jeopardy. Anybody knows about this particular challenge? Yeah, it was a while ago. Like I said, we're still in that previous era, right? So in this challenge, you had this quiz show called Jeopardy, and Jeopardy basically works by in a slightly different way, where you are given the answer, and you have to formulate the question. Okay. So in order to play the game, you have to have a pretty good sense of the world, trivia, factual knowledge, relationships between things, all of that. And the IBM Watson team competed in the game of Jeopardy against a couple of expert human Jeopardy players, and it won. Okay, and it was one of those very highly televised and exciting kind of events. And this was in some ways this was 2011, and so this was in some ways kind of the highlight of this structure prediction era, and being able to develop this kind of question answering system, right? And you do use question answering systems all the time on the internet. I mean, now you get an AI-powered response, but before that, you would also sometimes get just a summary or an answer to the question. So that was up to 2013, okay? And then things changed, because around 2013, you entered what was the deep neural networks era, okay? And again, 2013 is a bit arbitrary. Some people might contest this and say, oh no, it started much earlier. It kind of did. But the sort of craze which has now snowballed into what is now AI, I think started around the time. And so here, why I chose 2013 was because now, rather than rely on just these labeled data sets, you could now build models based on deep learning, which ingested just raw data. Not raw data, but large volumes of raw data, okay? And this became available around this time because you had the internet. And you also had computational power. Both these things came together. And around 2013 was this paper which was published, which described an algorithm called word-to-vec. And word-to-vec was essentially an algorithm which was used to derive a kind of representation, a vector representation of words. And the algorithm was able to do this from, of course, a large amount of data, but these vector representations captured some relationships between words, okay, without any explicit knowledge being provided to it. Remember, it's raw data now, that labeling stuff is gone. And it was quite interesting how it was able to do that simply by, with this intuition, this intuitive idea that when words occur next to each other, or you can tell something about the meaning of the word based on the words that occur next to it, okay? So simply by doing something where you take the vector for Paris, subtract the vector for France, and add the vector for Italy, you get Rome, okay? So in effect, what each word vector representation was capturing was something about that word meaning, okay? And so in this particular paper, you were able to do all of these kinds of simple vector additions and subtractions, and you can get very, very sort of, astonishing kind of results, right? Which tells you that here is an algorithm which can simply take in all this raw data and do much more with it. The representations that this early paper had were called static embeddings, okay? And this was just the beginning. Slowly, people realized that, look, we have this ambiguity in language, right? So you have that mouse-mouse problem. So if I have just one vector for one word, then that won't work, right? So I need something that's more contextualized. So people then came up with contextualized embeddings. They also made some other very interesting developments, advancements with respect to dealing with sentences of different lengths, which used to cause issues. And they also, there was also this, this invention of the attention mechanism, which led to the transformer models. And the transformer models are essentially your GPT, BERT models, which you, I'm sure, are aware of or heard of, or someone tried to do their homework using ChatGPT. How many people have tried? I don't know. But does it work? I don't think it works very well for maths. It does? Anyone tried it? Yeah, that's the problem. So then transformer models kind of came out of all of these different developments, and now these are known as foundation models, quite ironically, because actually the foundation of some of these ideas started maybe decades ago. But like I said, few things came together, like the availability of computational power and availability of lot of data. Now, one of the things in comparison to other eras, right, is that the models have less explanatory power. Less to, some might say none, because you can't really explain why they do well and why they don't do well. It's a bit of a black box. And that is partly because of the kind of complex architecture it has and the amount of data it is used to train on. So it is difficult, but it's not impossible. Nevertheless, far less explanatory power as to how, why it's working the way it is, okay? maybe you have also encountered this. You may have tried putting a prompt in ChatGPT and someone types in another prompt in a slightly different way, and you get some really bizarrely different answers. Anyone experienced that? I mean, this is the ChatGPT generation, so I thought maybe you guys know. The other challenge is that, again, multilinguality is a challenge, because now if you're saying that I have this large model, if I don't have enough of this raw data, right, then I can't really train it, right? So if I have a language which has very little presence on the internet, and I decide to train the model anyway, then that becomes challenging. So sometimes now people, what they do is train multilingual models. So if you have less of one language, you train lots of languages together. That's what they've done for many of the Indian languages. So we are in the deep neural network era, there's no doubt about it. But, and there is a lot of promise, there's a lot of excitement. I'm sure there are many of you who read about it all the time. And at the same time, there is also a lot of criticism. You know, what does it mean to have an AI do all the creative work? What does it mean for jobs and so many other things? What are some of the ethical and fairness implications? Within the field of computational linguistics, you start seeing papers like this. Has it all been solved? This was a paper from last year. I mean, it is sort of tongue-in-cheek, but nevertheless, you start wondering if the large language models are doing so well on all of these benchmarks, then should we just hang up our boots and just retire now? And then there have been also a lot of critiques with respect to, well, the language models are getting larger and larger, but are they really considering a lot of the different impacts that this has? What about the inequalities that it seems to enhance and so on? So there's a lot of discussion in the field around this. So in order to kind of talk to you about, you know, these models in detail, I actually want to go back to us as humans, okay? Because a lot of the time, the discussion in the, you know, in the public domain and also otherwise is that, oh, these are just like humans, right? They can communicate just like us. Or someone even said they have consciousness and then promptly got fired from his job, okay? So, so there are a lot of these kinds of stories around what these models can do. But I want to actually tell you that, well, there's a lot of difference between how humans, for instance, learn and how these models learn. But let's look at this problem with using a very little small sample of data, and that is the English past tense. Okay, so all of you know, most of you know English, of course, all of you know English. So when you have to learn the English past tense, imagine you were a child. And one of the ways you make the English past tense is to add ed, right? So you say walk, walked, okay? Jog, jogged, fax, faxed, spam, spammed, okay? You add ed to make the past. Then you have, but you also have all of these other forms, right? So you can also make the past tense with all of these other forms. So you have dig, dug, spin, spun, string, strung, okay? Stick, stuck, all of these. And while the vast majority of the verbs are formed, do create the past tense using the ed form, there's a decent number of these so-called irregular forms which don't follow the same pattern. Okay, and they seem to have some similarities between them, but it's not like it's not a very obvious pattern as to what it is. There's some sort of general trend as to how they behave. So these are maybe your exceptional cases, okay, but they exist. So a child, imagine learning language, has to essentially learn this. So how does the child do that? So there's one way. Here's one way. And let's call this the symbolic approach. Okay, so what does a child do? At some point, we know that the ED forms are the majority cases in the language. They're predictable. So you compute the regular rule of add ed to the verb whenever you have to compute the or create the past tense. And basically, there is a add ed rule to the end of the verb for this. For the other cases, you kind of store them in your lexicon and say, okay, whenever this is an exceptional case, let me kind of block this rule and look it up in my memory instead. So I have like a two-part system. There's a one that's working with the rules, the other one that's saying, okay, let me do the lookup. Okay, and this is of course assuming that the actual verbs forms like walk, jog, etc. in itself as symbols are learned along with those rules. Okay? Otherwise, this system doesn't make sense. Another way you might want to do this is say, okay, I don't care about the verbs, all right? What is regular, don't tell me all this. What I'll do is, I'll just look at the patterns of the endings, okay? So there is spin and spun, but like I know there's this in and un thing at the end. I just need to figure out that these two go together, okay? Then I have jog and jogged, but I actually don't sort of care about the jog part, all right? Just give me the endings, I can figure it out. So I just have to associate those endings with each other. Okay, then I'll learn. If I have a verb like hold and held, again, similarly, I just learn these, okay? And by associating these two, I can figure out what is the right ending. So I'm not really bothered about, okay, this one is regular, that one's regular, that's the exception, I need to store it. Doesn't matter, I'm just doing pattern association. So there's no difference, and there's no explicit coding of the actual verb, okay? So what do you think human children do? Okay, so this is do they use a symbolic approach, or do they use a sub-symbolic approach? Okay, so, okay, so let's see. So this was an experiment, that very famous experiment in linguistics, conducted by someone called Jean Burko. And she asked both adults and children, aged around 6 to 9 or so, to come into the lab and look at some of these examples of words, okay? So maybe you can participate in this. This is a wug. Now there is another one. There are two of them. There are two wugs, right? So you successfully applied some kind of plural formation, either a rule or you did something to correctly give me the form wugs. And all the children also did the same thing. But you have never seen, understood, or you don't know what this wug is, right? So Jean Burko also did this with the past tense verbs, okay, and something like this. So again, you remember there's a reason why they use these sort of made up verbs and made up words, because you want to sort of not confuse people or take into account these other factors that might interfere if you use a real word, okay, like table or chair or something, or run or walk or something. So this is the one with the verb. This is a man who knows how to spow. He's spowing. He did the same thing yesterday. What did he do yesterday? Yesterday he spowed. And that's exactly also what, well, most of them did that. Not all of them. Some, like a quarter of the children also said spowed. Okay. Here's another one. This is a man who knows how to gling. He's glinging. He did the same thing yesterday. What did he do yesterday? Yesterday he what? Glung, glinged, some variation, right? So So again, you saw something like that also in the responses. The kids didn't produce that many glings. The adults did though, because she did this on both adults and children. So what happened? What were some of the results of this study? So like you did, the 5-year-olds and 7-year-olds also produced wug-wugs and spore-spored. And but very few produce something like gling glang or gling glung, okay? As per maybe an analogy, if we go by the associative sort of approach, very few produce this, okay? And that would be in analogy to something like sing sang, right? Or ring rung. So many of you said glung. So that's because you were associating with something like ring rung, right? So at least it seems that maybe the children are basically using rule-based learning. Does it, at least on the surface of it, okay? And the kind of, uh, most of the time if they produce gling gling, it means that, okay, they've learned this ED rule, but that storage of the exceptional cases hasn't happened yet. That is one way to explain the data, that they're applying this ED rule, applying the ED rule. They didn't yet store the exceptions. So basically what they have is something like a symbolic system working there. Okay? But then people did some other studies. Okay, so what they did was to take very large examples of naturalistic child speech. Okay, so these are just interactions of kids with their caregivers, and then these are all transcribed and analyzed to understand what kind of forms are children producing. So here, they found that children also do produce these analogical kind of errors. So analogical errors, so why are the errors interesting? Well, the errors tell us something about what's being learned, right? So the errors tell us that if the child is producing bring brang or bring brung, then maybe the child is also doing some associative pattern matching with sing sang and ring rung. Otherwise, why would it produce those errors? So in that sense, there is not only a kind of rule-based symbolic strategy happening, but there's probably also a kind of associative pattern matching strategy that is happening. So simplifying this a bit, and by the way, there's a whole lot of literature on this, which I'm kind of condensing here. There seems to be some sort of evidence for the fact that children are, of course, learning by generalizing with rules. But they can also rely on other strategies like these associative sub-symbolic patterns, like the kind, like this bring brang kind of thing. So in other words, children are pretty flexible learners. They use whichever strategy makes sense, okay? And this has been found in other kinds of acquisition studies as well, where, where children, very small children, are first learning to segment words. Okay, so for example, if I say, oh, pretty baby, how do you know that pretty ends and baby begins? Why can't it be that the word is pretty baby and or something else, pretty bee, right? I could segment it either which way. As a child, the child has no clue, right? The child is very small. So how does the child know that it's pretty baby, right? So how does that word segmentation happen? Right? So what kind of patterns are the children learning? So again, a number of studies here have shown that there can be both a kind of statistical pattern association as well as a kind of a rule-based learning based on the tone, the prosody of the speaker. Okay. So long story short, it seems that children do employ both kinds of strategies. And but there's a bit of a difference between the two. Okay, and for both of these kinds of approaches, people have come up with models to see which kind of model explains the child language data the best, okay? And here what you find is that, with the symbolic approach, this deduction of the rule and the blocking of the exceptions is kind of important, right? Figuring out this is important. With the sub-symbolic approach, because there's no distinction, you have to rely on things like the frequency and the experience of the child. So the more often you encounter the forms, the more easily you will learn, right? So you will learn the ED form first because that's what occurs more often. And then you learn the exceptions later. And the point is that you learn gradually over time. There's no aha moment. I've learned the rule now. It's a bit different. So now given this background, well, I tried to ask ChatGPT to the same kind of a work test, and it gave me just possibly all the possible answers that it could think of. So it was not very enlightening. So let's come back to the question of, well, are these large language models like children? Are they learning like children? And the answer most certainly is no, right? Because for one thing, they have to learn from a huge amount of data as compared to humans, okay? A 12-year-old human is probably encountering less than 100 million words in their lifetime. Some of the largest language models are trained on trillions of tokens of data, okay? So that's several orders of magnitude more data than a human child will ever encounter. And yet, the human child is also becoming proficient in language over time, right? And the other thing is also that the large language model learning is primarily sub-symbolic in nature. It is not symbolic, it is sub-symbolic in nature. Although people are now innovating with different architectures that also have symbolic learning as part of it. The other thing that the language models can do is basically they are trained to do something very simple, which is predict the next word. Okay, that's a very simple training objective. Children, on the other hand, are motivated to do all kinds of things, or evolution has allowed them to use language to participate with other people in doing shared activities, to share goals and intentions. And particularly, these are things that distinguish humans from other kinds of social animals like apes. So these kinds of, and of course, children have the other added advantage of being embedded within a social context, being able to interact with other humans on a daily basis and so on, whereas there we have a very different kind of training and exposure and experience. So I don't have much time, but what if we then set aside the fact that, well, first of all, the language models are not like humans in terms of learning. They're doing something very different. They're in a different context. They don't learn from the same kind of data. But can we then examine them in terms of how they are understanding language? Can we just look at language understanding to see, well, what is the quality of language understanding they have? Okay. Again, with the caveat that the understanding that we have as humans is not the same as the understanding of these models. In popular articles, you often have these words like understanding, comprehension thrown around. But we have to keep in mind that they're not the same thing. Okay? I've just given you some examples to show you why. So let's take a look at this. So if these models have linguistic knowledge, then can we just ask them, hey, ChatGPT, can you tell me if this sentence is grammatical or not, right? So you will waste a lot of time if you do that, because if you want to really understand why something is likely to be a good sentence, even for a human, there are many factors involved. So you have things like the length of a sentence, the frequency of the words. If there are some highly frequent words, it's easier to understand. If it's plausible, so if it describes a scenario that makes sense or it's something completely bizarre, right? All of these factors play a role. So for both humans to test both knowledge in humans as well as models, we need to design a task quite carefully. And we want to isolate the phenomenon that we want to study a little bit so that we understand how it's really working. So here is one way, and it's not the only way, but it's a tried and tested way, which is via acceptability judgments. So what does acceptability judgments do? So let's take a look at these two examples. The keys to the cabinet are on the table. The keys to the cabinet is on the table. Okay? First sentence is okay. Second sentence, kind of off, right? Why is that? Is singular, it should be plural, right? Because it should be agreeing with the subject. So given this kind of pair of sentences, now I can compare the probabilities that the model is assigning to both the form are and the form is. Okay? And if the model understands agreement, so if it's figured out what is agreement, then the probability for R should be greater because this is the acceptable sentence, and is should be less probable. Okay? And essentially, we can do this comparison because everything else is the same. And it's just that part which is changed. Again, for Hindi, if we take a slightly different case, you have Meera ne aam khaya hai. It's fine. Some of you are not Hindi speakers, I know, but those of you who kind of comprehend it, Meera aam khaya hai. It's not okay, right? Because you generally require the ne over there. The ne is missing in the second sentence. Okay. So again, because in Hindi the verb is occurring last, you will try and do this calculation at khaya, okay, and compare. So so the hypothesis is that if there is an understanding of this kind of agreement, it should correctly also show in the probability that the language model assigns to it. And actually, the performance is very, very promising. At least for agreement phenomena, the performance has high accuracy across all the variants of this keys to the cabinet example that I just showed you. It's pretty high. And for Hindi also, for this particular pair that I just showed you, it shows very good, seems to show very good high accuracy in understanding the differences between these two sentences. And then people have tried and done this for other languages using these kinds of pairs, not just for agreement, but all sorts of other things, and found that, again, the results are very promising. But there are certain other phenomena in the last few minutes, I hope, I'm slightly over time, I hope it's okay, where this performance of these models is varied or not as robust. And I'll just give you a brief example of this and sort of end there. And that is to do with examples like these. So Rose wasn't disturbing Mark. That's fine. Okay. Rose wasn't boasting Mark. That's not okay, right? Why is it not okay? Any idea? Louder, please. Why is the second one not okay? Yeah, so boasting, like, you'll say Rose was boasting, then it's okay. But like you're saying Rose was boasting Mark, wasn't boasting Mark, well, what is Mark doing there? This is extra. The event of boasting just involves one person, right? So in this case, it's kind of not the right verb to put there in this kind of sentence. So now these sentences are a bit different from the other sentences because in those sentences you had to do this kind of matching, right? Is the number matching properly? Is the case and the verb form matching properly, right? This is a little different. It's not about matching, actually, but it's kind of about different kinds of events and different participants of those events. right? In one kind of sentence, that participant and event together is making sense. In the other one, it isn't. And so for humans, this task is quite simple. You quickly told me why it didn't work. But in some of these different experiments that I showed you earlier, in this particular kind of example, performance wasn't as robust. And so I'll show you a small task that we did for Hindi. And here it's slightly different from the acceptability judgment. It was a sentence completion task. Okay, so here you have a sentence. Mohan ne bachchi se pankhe se mombatti dash thi. How will you complete it? Louder. Bujhai thi. Okay, so if you're not a Hindi speaker, Mohan made the girl extinguish the candle with the fan. Okay? That makes sense, right? You took a fan and he told the girl to just extinguish the candle. But so this is what humans find okay, but we got completions like Mohan ne bachchi se pankhe se mombatti kharidi thi. Okay, weird. Mohan ne bachchi se pankhe se mombatti nikali thi. Quite difficult. Okay. And this wasn't there for, I should say, not a huge number of cases, but there was only 70% accuracy in little less than 70% accuracy in the task that we did. So about 30% of the cases, it was doing some stuff like this. So you need to know, you need to have some common sense knowledge about the world to understand that the fan will extinguish the candle, right? Or that you can't use the fan to remove a candle. Or that you can't really buy something with a fan, right? You need money, okay? So when you have events like these and particular participants, you actually need to do this integration of form and meaning. Because there's the form of the verb, they're the participants as well. They also have a particular situational meaning in the world. It's an event. So to do this, you need to integrate both form and meaning, and that is something which a language model trained on form alone finds sometimes difficult, okay? And one of the things that is kind of the challenge here is that this common sense knowledge or grounding is something that the language models don't have. And when we learn and use language, we are sort of embedded in a world which has, communicative partners, goals, right? And here you just have, there's also the perception and the physics of the world, of the real world, which we don't have, which the model does not have access to. And, but interestingly to note that in our experiment with the fan and the candle, not all the answers were bad, right? So only part of the answers were kind of awful with the buying and the other things. So the interesting research questions are, well, how much of this common sense knowledge or grounding is needed? How much of it do we need, right, to understand something? And how much of all meaning requires this real world knowledge? And how can you infuse it into a model that is trained only on text? And these are some of the very interesting research questions that are focusing on these problems, trying to develop better representations for integrating both form and meaning. So I'll just end here. I'm over time, I know. But essentially, to just summarize my talk, one of the challenges that we started off with was to integrate both form and meaning. That is the challenge in computational linguistics or even linguistics in general. And we are in the neural networks era, which shows a lot of promise. But we need to address a lot of different kinds of criticisms from the point of view of multilinguality, from the point of view of interpretability, and more largely speaking, also ethics and fairness. We also need to keep in mind that whenever we look at the public discourse about these models, which compare them and say they are just like us, they are not. They are very different kinds of learners. They also do not make the same kinds of mistakes as you just saw. So we need to evaluate and understand their promise, their capabilities, and learn more linguistics to ignore the hype and understand what all they are able to do. So I'll end here. You have questions?
Thanks for delivering such an amazing talk. Do we have any questions from the audience?
Yeah.
So my question is that uh, can we use this model to generate a new language? Something that can maybe substitute encryption decryption. But decryption is not a language in its own, but can it create a new language?
Well, that's a good question. I don't know of actual work which has tried to do that, but I would imagine that given enough examples of different kinds of grammars, potentially it could invent a new language. I mean, it is again what kind of language model, you know, I think it's possible, but I haven't tried it. So I can't exactly answer you. But inventing new languages is something we are pretty good at. We've done that with Esperanto, for example, which is an artificially created language. We write new programming languages all the time, right? New programming languages come up all the time, which are not natural language, but nevertheless. And as humans also, we generate new languages because different varieties can come together and a new language can emerge. So I think it's possible, but I guess I don't have a direct, definitive answer for you. Yeah.
My doubt is about, the neural networks era, which was talked about. So recently, the Nobel Prize for Physics went on the neural network research itself. I did do a little bit of research because I was curious on why the Nobel Prize of Physics went to like computer scientists. Because from outside, when you see neural networks, it did seem like a computer science topic. So why did they give the Nobel Prize of Physics for it? I didn't understand. I did understand that as background, they were actually like psychologists and physicists only. But I quite didn't get the fact why they still did give it though, because in core neural networks is computer science only, right?
Yeah, I think so. I mean, I don't know the Nobel Prize Committee's reason. I don't know, they don't have a subject like computer science, perhaps that is why. But as far as neural networks are concerned, they actually have a pretty long history. So some of the developments that are happening now, right, which are so much at the forefront, people have been working on them for a long time prior to that. And some of those, have had their limitations. So you had, at that time, less availability of data and computational power. So they could not really develop the way they have now. But the ideas have been around for a long time. And my understanding is that this was, the prize was probably given. I mean, I don't know about the subject. I don't want to comment on that. But some of the fundamental work on some of these ideas it was probably done in order to recognize the work that was done then.
Okay, then another question. In general, there's this ML and AI craze which is going on also.
Yeah.
Machine learning in general does use a high amount of maths, and so I understand the utilization of maths in the neural networks and stuff.
Yes.
How is physics coming to play a role in it? Like, if there is any examples you could, because obviously I'm an elementary in both the subjects at hand, so I just want to know how they can get related.
Are you asking in relation to the Nobel Prize or?
No, in general.
In general. Oh, so yes. So for example, things like, understanding, when you think about events, right? For example, you think about the event of jumping, right? When you jump, you go high up in the air and you fall down, right? If there's a sort of trajectory, right, that you might follow, you expect, right? And that is because of the way, well, gravity works, the weight of the human body, and so on. Similarly, things falling down and so on. The way you might grasp different objects based on their weight, right? So all of these things require an understanding of the world, of the way the laws of the natural world work. And that isn't something that is, again, with language models, it's never explicitly told, right? So remember, the whole sort of excitement about these large language models is because you just take a lot of raw data and here you go, okay, understanding. But a lot of these aspects are in fact not explicitly there, right? So in order to explicitly teach those, you would have to come up with a model, a way to sort of train the model so that this is actually learned, right? All of these different relationships or laws, you can say.
Are there any more questions? Then let us thank her again.
Thank you very much.